welcome back to AGT STEM. Today we're going to be watching a video about technetium. So, without further ado, let's hop to it.
One of the big surprises of the whole periodic video project for me was my actually seeing a sample of technetium. Before I tell you how I saw it, let me explain why I was surprised. Technetium was one of 4 elements that were predicted by Mendeleev to exist in the periodic table, but had not yet been discovered. He predicted it first to have an atomic weight of 100, which he then revised to 99, which was pretty accurate. So technetium is element 43, and obviously between molybdenum, which is 42, and rhenium, which is 44. The real discovery came when 2 Italians, Emilio Segre and Carlo Perrier, in Palermo in Sicily, were sent a sample of molybdenum that had been irradiated in the cyclotron in Berkeley. It had been irradiated with a mixture of neutrons and deuterons. Deuterons are the nucleus of deuterium, 1 proton, 1 neutron. And so Segre and Perrier were dissolving up this piece of molybdenum, which was highly radioactive, so they let it sit for a bit so some of the radioactivity decayed, just to find what was in it. By carefully precipitating and seeing where the radioactivity went, they isolated the first sample of technetium. But it was too small to see, but by its behavior and the fact that it precipitated together with rhenium, they could tell that it must be in the same group. I think it was just sent to them because they were interested. Nobody expected technetium to be in it. And the technetium...
The power of curiosity can discover whole new things.
...was therefore the first element that had ever been made synthetically. Chemists who were looking at the structure of the periodic table felt that synthetic elements were somehow cheating, so it should not be put on the periodic table. Can you imagine that? The paper was published in 1937, and nothing happened till the Second World War. Then, in the Second World War, there was the Manhattan Project, the development of nuclear weapons, and lots of new synthetic elements were discovered, particularly plutonium, which had never been discovered before. And after the war, 1947, very shortly before I was born, there was a historic paper was published in the journal Nature by the German chemist Paneth, who during Nazi times had moved to the UK and was working at the University of Durham. He laid down the ground rules which exist to this day for the naming of elements. Number 1, the right to name an element should go to the first, presumably group or person, to give definite proof of the existence of one of its isotopes. Second point, in deciding the priority of the discovery, there should be no discrimination between naturally occurring and artificially produced isotopes. And the third point, and this is very important, if a claim to such a discovery has been accepted in the past but is refuted, that means contradicted, by later research, the name should be deleted and replaced by one chosen by the real discoverer. And those rules applied to this day. And it was technetium that really precipitated this. So what happened then was that the names of 6 new elements, including plutonium, were accepted, and Segre and Perrier were invited to name their element, and they chose the name technetium in the same journal in a really short paper from the Greek word which means synthetic. So it is embodied in his name that it was the first synthetic element. In the early 1960s, with the improvement of instrumentation, people discovered that in uranium minerals, because of the radioactive decay of uranium, you can detect tiny, tiny traces of technetium. And therefore, it is natural after all. So the name isn't quite right. And then in 1972, there was an extraordinary discovery by geologists in Gabon in Africa, where they discovered that in a uranium deposit underground about 1 million years ago, a natural nuclear reactor had started. There was a high enough concentration of uranium for a nuclear reaction to take place, and because of this nuclear reaction, there were in fact traces of technetium found under the ground. Because of all the nuclear research that was done during the Manhattan Project, there was an abundant supply of technetium became available after the Second World War, and people started studying the chemistry. And you can get a wide range of compounds. And as you might expect, the chemistry is perhaps a little closer to rhenium than to manganese, because heavier elements tend to be more similar. But one of the most interesting applications turns out to be in medicine. The application is in diagnosis. When people have cancer, it's often quite hard to see the tumours, or particularly the secondary tumours that spread across somebody's body, because they're small and they are not easily imaged. But it turns out that if you take radioactive molybdenum 99, it decays by emission of electrons to make technetium. But very unusually, and something which we've never talked about before, the technetium is formed with a nucleus in an excited state, that is, with higher energy than it might have otherwise. And this excited state is symbolized by the letter M, which stands for metastable, which means it's stable for a short time but not very long. And so what happens is this metastable technetium decays to the stable isotope, or stable state, but with the same mass, and gives out a gamma ray which can penetrate a large distance through, for example, human flesh. And then much more slowly, the technetium 99 decays to ruthenium. So what happens is that if you do your chemistry very quickly, you can isolate this technetium 99M, and before it decays, you can react it with another chemical which will complex, that's bind round the technetium, and you choose this binding chemical so that it will also bind to tumour cells. Selectively, it will bind to the tumour and not to ordinary organs. So quickly you inject it into the patient, it goes round the body and is localised at the tumours. Then if you put the patient into a suitable detector or array of detectors, you can measure the gamma rays coming out, and the gamma rays will come out much more strongly from where the tumours are. And because the technetium decays rapidly, you can get a good signal to do your imaging without giving the patient a big overall dose of radioactivity.
So technetium can help diagnose cancer.
So now this brings me back to how I saw technetium. Some years ago, I went to Zurich University and met a professor, Roger Alberto, who is one of the world's experts in technetium chemistry. During the coffee break, Roger came up to me and pulled out of his pocket a little metal vial and unscrewed the lid and took out a glass container, and inside was a piece of metal coated with technetium. I was amazed. I never thought I would be able to see this. So I immediately asked him how he could get hold of this stuff. And he explained that one of his co-workers had used electrolysis, that's passing electric current through a solution, to deposit a thin layer of technetium onto a piece of copper. Now, you don't need very much metal, only a few nanometers, to see what the metal looks like, because light doesn't go through it. And in fact, this particular sample, I think, had probably a couple of milligrams of technetium on it. So it looked just the same as a large block of technetium would look. But I felt really excited because here was an element which I'd seen sort of in brackets on the periodic table, and I never thought I would actually hold a sample in my hand, or I held the glass bottle. And because technetium decays by beta emission that's emitting electrons, and these electrons don't penetrate through material very easily, even a small glass vial is quite enough to protect people, at least for a short time. So I could safely hold it, and in triumph, I held it against my tie next to the symbol of technetium, and I felt I'd really made a discovery.
Thank you so much for watching. We'll see you next time. Stay smart. Bye!